All right. Okay. Well, happy Friday, and we shall. I guess we'll get started here. Okay. All right. So, yeah, midterm exam on Monday. So this weekend I'll send out a seating chart. So just be on the lookout for a seating chart, and I think all the seats have numbers on them, and there technically are like row labels. But I guess a lot of the row letters have fallen off. So, I'll just send out the seating chart, and I think I've got it to match up. So hopefully that will work. It's a little weird. This side is 135, and that side is 246, and then in the middle you have like 101 through like 111. But anyway, that's that. Okay. All right. Well, today we are going to take a look at rejection sampling. Rejection sampling is a method for us to generate random values from a given distribution. So remember that kind of the context in which all of this is coming from is that one of the big methods we use is Monte Carlo integration, Monte Carlo estimation, where we generate a bunch of random values from some given distribution, and we use that to estimate, some kind of quantity. So whether that be the expected value of a distribution, or what would happen if you plug that expected value, or not expected value, if you plug those random values into a function like h of x, whatever that h of x is, you can plug in the random values and then get the expected value of that function. We've been relying on R's ability to generate random values, and R has a lot of kind of built-in functions. We have R binom and R beta and R whatever for a lot of these things. And then on Monday and Wednesday, we said sometimes we want to generate values from a different distribution, and one way we can do that is the inverse CDF method. That requires us to find the CDF and then to invert it, and then you just plug in a random uniform into the inverse CDF, okay? Today's method is another way for us to generate random values from a distribution. This one does not require finding the CDF, does not require finding the inverse of the CDF, okay? So, famously, the normal distribution doesn't have a closed form solution for the CDF, and therefore we also won't have a closed form solution for the inverse of the CDF. Now, our computers kind of work around this and just use an approximation that's accurate up to 16 decimal places, and we say, okay, well, that's good enough for our computers. But if we were in a situation where we needed more than 16 places of decimal accuracy or something, I don't know. How would this work, right? Because we don't have a solution for the CDF, okay? So for something like that, we can use rejection sampling, okay? So the goal is still the same. We want to get random values from some distribution, okay? Some distribution. All we have is the PDF. Okay, we have the PDF, but we can't, either we don't want to figure out the CDF because it's too hard, or we can't figure out the CDF because, something, okay? So we don't know, the problem is we don't know the inverse CDF, so we can't use inverse CDF method, right? If you know the inverse CDF, then inverse CDF is a good method to use. But we're going to say, well, here's a situation where we don't know the inverse CDF, or it's too hard for us to work with the inverse CDF. Okay, so what we're going to do instead, this is what we're going to do. We're going to generate random values from a different distribution. We've got what we call a candidate distribution, g of x, and we are going to generate random values from g of x. So this is a distribution that we are able to sample from, okay? And the requirement is that the support of F must be fully contained inside the support of G. So this sounds a lot like importance sampling. Okay, so if you remember importance sampling, we say, well, we don't know how to work with F directly, so we're going to work with G instead, and then the support of F has to be contained within the support G. So there's a lot of kind of parallels here. The key difference, though, is that importance sampling, and again, I don't like that name, importance sampling, but importance sampling is used kind of as a form of Monte Carlo estimation, where we are weighting the values we get to estimate whatever integral that we have. So we have Monte Carlo integration, Monte Carlo estimation, and importance sampling is a workaround that we can use to, if we can't sample from F, we sample from G, and then we weight all of our values accordingly. Okay. Rejection sampling, however, is I want to generate a random sample. And when you want to generate a random sample, we're going to just kind of generate random values from G, and then we're going to throw away some of the values from G so that what remains is a sample from F. Okay, so that's rejection sampling. That's where the rejection comes from. So we generate random values from G, and we say, well, we're sampling too many of these values, so we're going to just throw these ones away. Okay, and then after we throw away a bunch of values, then what remains looks like a random sample from F. Okay, so anyway, this is what we need. So we have a distribution G that we are able to sample from. F has to be the support of F has to be fully contained within the support of G. And then the other thing is there has to be some constant M, a constant that is less than infinity, okay, such that when you multiply M times the PDF G, it is greater than or equal to the PDF of F for all values of X. Okay, so this is important. So there are some kind of cases where you have G and F, like the support of F is fully contained within the support of G, but then when you search for this constant M, it's like, asymptotically, like that M has to go to like infinity, and that's just not going to work. Okay, so there has to be some finite constant M such that M times G is going to be greater than F for all X. Okay. Because we require M times G of X to be greater than F of X, the most efficient choice of M, okay, is to find the ratio of F divided by G, find the maximum value. So if you, this might be tough to figure out, but if you can do F divided by G and figure out what is the max of this thing, okay, then whatever you use here will satisfy this condition, and will be the most efficient choice. Okay, if you use anything smaller than that, then that means there's going to be some value of X where M times G of X is not greater than F of X. Okay, if you don't use this value. All right, and this is how it's going to work. We're going to generate random values from G of X. Okay. We generate random values from G of X, and then for every value, we calculate this ratio, which is going to be F divided by M times G of X. All right, and remember, because M times G of X is greater than F for all X, this ratio will always be less than or equal to 1. Okay, so this is always going to be less than or equal to 1, and then we generate a random uniform value between 0 and 1, and if that random uniform value is less than R of X, then we will accept whatever X value that we generated. Okay. However, if the random U is greater than this R of X, then we throw that value away. Okay, we reject it. We reject that value, and that we don't accept that. So depending on what your M is and depending on what F and G are, you might generate 1 million values from G, and you might only accept half of them, okay? And so your random sample ends up being, you only have 500,000 values, okay? but those 500,000 values will come from the distribution F. So that's rejection sampling. You're going to generate more than what you need. Okay, you throw away some of them, and then what you have remaining will come from the desired distribution F. So let's try an example. Okay, we have the beta 2,2 distribution. Okay, and so remember, when you have beta with shape parameters A and B, you've got this, you got this constant, and then it's going to be what letter did I use? X. Okay, x to the a minus 1 times 1 minus x to the beta minus 1 or b minus 1. Okay, I think in our theta binomial we use theta instead of x. Don't get confused that we're changing our letters here. Okay, so if you just plug in 2, if you get shape parameters 2 and 2, this just becomes x times 1 minus x, and then this thing computes out to be 6. Okay, so basically it's just this upside down parabola. So you have this upside down parabola, but when you integrate it, it integrates to 1. Okay, now we can generate values from this thing directly with R using R beta. Also, this is simple enough where we could get the CDF and do inverse CDF. Okay, so it's a little bit wasteful and a little bit silly to use rejection sampling, but we'll just do a demonstration here. Okay, and so for our candidate distribution, we'll use the uniform. Okay, and the uniform distribution has a PDF that looks like this. Okay, so that so this is the uniform. This PDF of the uniform, and then this is up here we have the PDF of the uniform. Okay, so total. I don't know if this is accurate, but the total area of this thing should be 1. The total area of the rectangle is 1. The total area of this upside down parabola also 1. But these work because the support of G is fully contained within so the support of F is fully contained within the support of G. All right, because they're the same support, 0 to 1, 0 to 1. Okay, so this is what it looks like, and what we need is we need to multiply g of x, okay, which is going to be the uniform, by some constant so that it is greater than f of x for all values of x. Okay, so basically we just have to kind of find out like what is the max value here, all right, and that's going to be like 1.5, and so I'm going to multiply the PDF of our uniform by 1.5. Okay, and then it'll be greater than f of x for all x. Okay, so we can do that. Okay, all right. Oh, yeah. So this is our solution here. Okay, so the most efficient choice of m is the max of f of x divided by g of x. So our f of x is 6x times 1 minus x. G of x is 1, and if I do f of x divided by g of x, we get this, and then we're going to find the maximum value of that. The max value occurs when x is equal to 0.5, and when you plug that in, the value of m is going to be 1.5. Okay, f of x divided by g of x, plugging in 0.5, you get 1.5. Okay, so when you multiply g of x by 1.5, it just pushes it up here. Okay, and so now we have this here. Okay. And then we're going to, what we're going to do is we're going to generate random values from the uniform distribution from 0 to 1. And then we're only going to keep some of them. So So the way it's going to work is for each value, I'm going to just generate like a random value. Okay, so let's say I generated x comes from the uniform, and I get I don't know 0.3. Okay, and then I'm going to calculate this ratio of, so basically g of x, m times g of x is 1.5 for everything, and then f of x is 6 times x times 1 minus x. All right, so if I plug in 0.3, I don't know what I get. I get 0.3 times 0.7 times 6. What is this? Okay, so 0.21 times 6, 1.26, is that right? Okay, so I'm going to get 1.26 divided by 1.5. Okay, well, I don't know what that ratio is. Okay, so r of 0.3. Okay, 1.2. I don't know what that is. Like 0.8? 0.83? No, 0.8 something. Okay. We're going to generate a random value of u. Okay. So this ratio somewhere around here. Okay. It's like 0.8-ish. All right. And then we generate a random value of u. So if the random value of u is less than 0.8, okay, then we will keep it. Okay, but if I generate a random value of u that's between here and here, then it gets rejected. So every time I generate, say, 0.3, I'm only going to accept it with the probability of this kind of ratio, this whatever this 1.26, I think it's 0.84, is that right? I don't know. Someone do the math here for me. And so we're only going to keep some of these values, all right? So, because the uniform, it generates 0.3 a little bit too much compared to the actual f, right? F says it's only should create this much, and the uniform is creating it this many times, okay? Versus over here, say like values near 0.1, okay? 0.1 is going to be 6 times 0.1 times 0.9, we're going to get like 0.54 divided by 1.5. That's, I don't know, 0.3 something, okay? And so, these values should only get accepted like 30% of the time. So if we generate a 0.1, the uniform is generating 0.1 like 3 times as often as what f of x should, okay? So we use this random uniform to just say we're only going to accept some of the values that we've generated, okay? Because g is generating some of them too much, okay? And so those ones that it generates too much, we throw those away. So we're going to compare u to this ratio r, and then accept only some of them. So after we've thrown away some of our values, this is the values of x that we've accepted. Okay, so here I have all of my proposed x. There's 100,000 of these things, 10 to the 5. Okay, and then the accepted values of x is just a subset of the proposed values of x. Okay, so the accepted is going to be a true/false, right? I have a value of r of x calculated for every single proposed value of x, found by doing f of x divided by m times g of x. And then I generate 100,000 random uniform values, and then I'm going to get a vector of true/false values, logical values, 100,000 of these things, some of them true, some of them false, and I only keep the ones where the accepted is true. And so some of those values get thrown away, and we can see that as far as the values that get kept, all right, here's a histogram of the values that got kept. It follows the distribution that we expect, okay? That follows the beta distribution. All right, here I can plot the theoretic beta distribution, P beta, with shape parameters 2, 2. And here's the empirical CDF, okay, in black plotted on it. And we can see there's a very close alignment between these two things. So that's a good sign. Here's a little bit of a kind of an illustration. Sorry. Here's a little bit of an illustration of how it works, okay? So the dots here are a plotting of the random value of x generated from g of x and the random coordinate u, okay? So u can go anywhere from 0 to 1, right? So the top would be 1, okay? And basically, if that u is greater than f of x divided by m times g of x, okay, then it's going to end up in here, and I colored those dots red to indicate that these ones got rejected. And then when it ends up below the curve, I colored those dots black to indicate that they got accepted, okay? So these values got accepted, these values get rejected, so you can see some of the values get thrown away. And so what we end up getting, what we end up keeping will follow the desired distribution. All right, let me give you your first view quiz answer, which is the letter C, C as in cat. C as in cat. Okay. So the empirical acceptance rate is how many values that we accepted divided by how many values we proposed. So we proposed 100,000 values, and we ended up keeping 66,658. Okay, so we ended up throwing away around a third of our values. The theoretic acceptance rate is going to be 1 over m. Okay, and that's because if you think about what is the area of g of x is 1. The area of f of x is 1. But what we had to do is we had to multiply g of x by m so that m times g of x is greater than or equal to f for everywhere. So the area of g of x ends up being m, right? 1 times m. So the area of m times g of x is m. The area of m times g of x that's covered by f is going to be 1 over m. So we're only going to accept basically 1 over m of those values. The proportion of m times g of x that is covered by f of x is 1 over m. So theoretically, this is how much we're going to accept. So we accept around 2/3, and that's what we end up getting. Okay. All right. Here's another example. Okay. Again, kind of similar in shape, except we're not going from 0 to 1. We're going to say the PDF that we want to generate from is sine of x, okay? And our support is going to be 0 to pi over 2, okay? So we're going to go from 0 to pi half, and we're going to generate values from the uniform distribution. And in order for the support of f to fall within the support of g, our uniform distribution will go from 0 to pi half. Okay, and so the PDF of this is going to be 2 over pi. Okay, and then we want to find a value of m such that m times g of x is greater than f of x for all values of x. Okay, well, sine of x has a max of 1. Okay, and then so basically I just need to multiply this thing by pi over 2. Okay, and this is what it looks like. So when you go from 0 to pi over 2, sine of x looks like this. Okay, the corresponding uniform distribution has a PDF of 2 over pi, which is a little over 0.6. Okay, and then when you multiply that by pi over 2, then the max value is there is 1. So this is what it looks like. Okay. And what we're going to do is we're going to generate values from 0 to whatever, pi over 2, 1.5-ish, okay, uniformly, but we only want to keep the values that fall under the red line. Okay. So we're going to end up throwing away, you know, almost half of our values. We're going to throw away a good portion of our values here. Okay. So again, I'm generating 100,000 values here from the uniform distribution. We're going to calculate this ratio, the proposed value of x divided by m times g of x, and in this case, m times g of x is just 1, okay? It's just this blue line up here, okay? Some of those values will be, we're going to generate 100,000 random uniform values. Some of those random uniform values will be less than this ratio that we've calculated, and so we're going to get a logical vector of true and false values, and we will accept only those with true. So our accepted vector x is shorter than our proposed vector, but indeed this is what we end up keeping, and this looks like what we want. Okay, so we generated values from 0 to pi over 2 uniformly, but then a lot of these values, especially the values around 0, just got thrown away. Okay, here is the histogram and the corresponding density. Here is the empirical CDF and the theoretic CDF. Okay, so the theoretic CDF is the integral of that, so 1 minus cosine of x. All right, looks like that, and we get close matchup, so that looks good. We could do a KS test. We don't have to. Just again, a plot of what we've generated, what we've kept, and what we've thrown away. And we can see, yeah, we're throwing away a lot of our values. Okay. And we have that. Okay. So here, so far, we've been just kind of like our generating distribution has been the uniform distribution, which is simple enough for us to understand. But the uniform distribution is not going to work if we have something like the normal distribution, okay? Because the normal distribution, its support goes from negative infinity to positive infinity, okay? So you can't have a uniform distribution that goes from negative infinity to positive infinity because the PDF there would be 0, okay? And that's just not going to work. So we have to use something else. Okay. So here we've got the folded normal distribution. Okay, and again, for the folded normal distribution, it's we're taking the basically the normal distribution, and then we'll take the standard normal distribution, and then we'll plug it into an absolute value function. Okay, and so when we do that, if it's centered at 0, our PDF is just 2 times the PDF of the standard normal. Okay, because the total area still has to integrate to 1. So we have that. Okay, and then for a candidate distribution, we're going to use the exponential distribution, okay, which is going to be e to the negative x, exponential with lambda 1, rate parameter 1, and that will be e to the negative x. And these have the support of f is fully contained within the support of g, so that works. And then we can also calculate a value m such that m times g of x will be always greater than or equal to f of x. Okay. So this is, in red, we have the PDF of the folded normal. Okay, and then, and so this is basically, this is 2 times the normal density in F, in red, and then in G is the density of the exponential distribution, so I just have d exponential right there, and we can see that has that, and then this is okay because what do you call it? The f decays at a rate of basically negative x squared, whereas g decays at a rate of negative x. So the g of x is always going to be greater than f of x, once you get out past a certain value here, okay? All right, so we need to find a ratio, a value of m, such that when I multiply m times the yellow line or the orange line, it's going to be always greater than the red line, okay? And so we need to figure out this value m so that when I do m times g of x, it's always greater than f of x. And so the most efficient value to use there is to find what is the maximum value of f divided by g. Okay? So f of x has this PDF, and g of x has this PDF, okay? And so we can kind of do a little bit of algebra here, all right? And we want to find, okay, well, where is the max of this? So I've got this quantity 2 over root 2 pi e to the negative x squared divided by 2 minus x, okay? All right, so so basically the max of this quantity e to the negative this is going to occur at the minimum of x squared over 2 minus x, okay? Where does the minimum of that occur? And you can see, oh, okay, well, the minimum of this thing is going to occur at x equal to 1, right? Because this is just a parabola, and where is the minimum of that? The minimum of that is when x is equal to 1. So if I plug in 1 back into this, and I say, all right, what is this going to be? Then m is going to be 2 divided by root 2 pi e to the negative 1/2 minus 1. Okay, and so e to the 1/2, 2 over root 2 pi. We get m around 1.32. Okay, and m of around 1.32 is going to be the value that we use. And so when I multiply g of x times 1.32 m, I get this blue line right here. Okay, and we can see that the blue line is now indeed greater than the red line for all values of x. Okay, and technically this goes on to infinity, but we can just see asymptotically this blue line is always going to be greater than the red line as well. Okay, so we have this. Okay, and so now we will try this out again. Okay, so I will generate random values from g of x. So this time I'm generating 100,000 values from the exponential distribution. So I'm generating values from basically this orange thing. So we're going to generate a lot of values near 0, not quite enough values near 1, and then kind of too many values greater than 2, 3, or 4, right? And we're going to just kind of keep some of these values, okay? So I generate random uniform numbers, 100,000 of these things, and then we're going to say, is that u less than r of x? Okay, we calculate this ratio for every single value that we've generated. We ask, is u less than that? Some of them will be true, some will not, and we only keep the proposed values for where u is less than that. Okay, and so when we do that, the resulting sample that we keep follows the distribution that we want. Okay, the histogram of this. So again, we're generating from a different distribution, g of x, not f of x, but we just throw away. So the exponential distribution is going to generate a whole bunch of values near 0, and we just end up throwing a whole bunch of those away. Okay. And as far as the ones we keep, they follow the distribution that we want. Okay, and similarly, the exponential, it doesn't generate a ton of values near 4, but it'll generate, the exponential value distribution will generate some values near 4, whereas the normal distribution almost never generates values near 4. Okay, so anytime the exponential distribution generates a value of 4, probably we're going to throw it away. I mean, very rarely will we keep it, but almost certainly we'll throw it away. And then so that's how we kind of reduce it down to look like the normal distribution. Okay, again, we can kind of do a check to see if the CDF and the empirical CDF match up. So the theoretic CDF is going to be twice our normal density, okay? Twice the, basically the right-hand side of the normal CDF, so 2 times P norm, and then -1 so that everything, caps out at 1, so it looks like that. And we plot that against our empirical CDF, and we have a good matchup there. And again, here's a plot of kind of the random values that we've generated. And again, we accept only some of them. So we've generated values. So again, the exponential distribution doesn't frequently generate values near 4 or 5, but occasionally it does. Okay, but again, compared to the normal distribution, the normal distribution almost never generates values near that. So we end up kind of throwing, almost every single one of those values away. Okay. Let me give you your, I guess I'll go ahead and give you your last 2 view quiz answers. We'll give them both in the video too. Answers are C and D. C as in cat and D as in dog, okay? Second answer is C, third answer is D. Okay, so this is rejection sampling. Let me just do like a quick demo in R. Let me just do 10 of these things, okay? So when we look at kind of our proposed values of x, just round off to say 3 decimal places, okay? We can see with the exponential distribution, occasionally, not frequently, it's going to generate a value like 2.895, okay? Whereas what I need to do is I need to calculate the PDFs of these things, okay? And so the acceptance ratio so let me just plot the proposed values of x and the acceptance ratios. So you can see this value 2.895, okay? Because the exponential distribution generates this at a rate that's much greater than what the normal distribution would, the acceptance ratio of this is only around 0.165, okay? So first of all, the exponential distribution doesn't generate values of 2.895 very frequently, but when it does, it only is going to get accepted around 0.165 of the time. And so, when you multiply the PDF of this generating distribution, g of x, times basically its acceptance ratio, and the acceptance ratio is found by doing f divided by m times g of x. When you do that, you end up getting the desired distribution of f, okay? Whereas, values like 0.957, okay, values around 1, they get accepted like with 100%, almost 100% of the time, okay? Because when you compare these things, okay, the normal distribution produces values around 1, more frequently than what the exponential distribution does on its own, okay? And so what we've done is we've scaled up the exponential distribution up to here, and so we can see that the acceptance ratio right around here, right around 1, okay, is going to be at 100%, okay? Whereas values around, closer to 3, 2.89, this gets accepted, kind of very rarely. So this is kind of a plot right here. And so, yeah, values like 1.18 get accepted with high probability. Values of around 0.14, okay, values close to 0, the exponential distribution, again, generates these a little bit too frequently, and so we only accept some of them. And that's what we have, okay? All right, so if you look at the actual numbers themselves, you can see how often this goes. And then so when I generate 10 values from the uniform distribution, okay, we can see, do these get accepted or rejected? So I'm going to compare U to R sub x. All right, so these are the random uniform values. This is our acceptance rate. And so we can say, all right, so this one got accepted. The value at 2.895, it should get accepted only 16% of the time. The random value we generated was 0.87, so it's going to get rejected. Okay, whereas everything else actually got accepted. But this one got rejected there. Okay, all right. Okay, we'll wrap things up here. This is rejection sampling. I think it's in your homework, but or maybe in the next homework. So we'll have that. Okay, good luck as you guys study, and we'll see you on Monday for the midterm exam.